Hello everyone, this is Rahmat Ali from Indirapuram Public School. In the previous session, we have learned about the magnetic field, Biot-Savart law, certain applications of Biot-Savart law, and we discussed Ampere's Circuital law. Today, we will study about certain applications of Ampere's Circuital law. We will study about the force on a current carrying conductor passing through any magnetic field, Lorentz law, and cyclotron. So let's begin with the application of Ampere's Circuital law, that is magnetic field at a point due to a long straight current carrying conductor. Let V have a long straight conductor carrying current I. If we have to calculate magnetic field B at a distance r from it, then we consider a loop of radius r around the conductor. Line integration of magnetic field B dot dl around the conductor will be equals to integration B dot dl. As B is constant over the loop, so integration B dot dl equals to B integration dl. We know integration of dl over the whole loop is equal to 2 pi r. So integration B dot dl equals to B into 2 pi r. See, this is equation number 1. According to Ampere's Circuital law, line integration of B dot dl equals to mu naught times I. This is equation number 2. From equation number 1 and 2, we get B equals to mu naught upon 4 pi 2I upon r. Magnetic field at a point due to cylindrical conductor. Proof. Let V have a long straight cylindrical conductor of radius capital R. It is carrying current I. If we have to calculate magnetic field at a point P outside the conductor at a distance small r, which is greater than the radius of the cylinder capital R, from it, then we consider an Amperian loop of radius r. Line integration of the magnetic field will be equals to integration B dot dl, as B is constant, so line integration B dot dl equals to B integration dl. Once again, the integration of dl will be equals to 2 pi r, so integration B dot dl equals to B into 2 pi r. According to Ampere's Circuital law, integration B dot dl equals to mu naught times I. From equation number 1 and 2, we get B equals to mu naught upon 4 pi 2I upon r. If the point P exists at the body of the cylinder, that means small r equals to capital R, then B equals to mu naught upon 4 pi 2I upon r. If the point P exists within the body of the cylinder, that is small r is less than capital R, then there exist two situations. Let's study the situation 1. If the cylinder is hollow, then current enclosed within the loop will be 0, because now the current is passing outside the body. So I equals to 0, that means B, the magnetic field, will be 0. The graph represents the variation of magnetic field with the distance. In the graph, we observe that the magnetic field from distance r equals to 0 to the radius of the cylinder capital R is 0. At small r equals to capital R, the magnetic field is maximum. Beyond r equals to capital R, if we obtain the value of B, then we observe that B is inversely proportional to r square. The graph is indicating it very clearly. Situation 2. If the cylinder is solid, then current will also pass through the shaded area of the loop shown in the diagram. If current I is passing through whole area pi r square of the cylinder, then current through the shaded area I dash will be equals to I divided by pi r square into area of the shaded loop. As a result, we get I dash equals to I divided by pi r square into pi r square. Here small pi r square is equal to the area of the shaded loop. Substituting this value of the current in the magnetic field, B equals to mu naught upon 4 pi 2 I dash upon r. We get B equals to mu naught upon 4 pi 2 I into r divided by capital R square. The graph represents the variation of magnetic field B with the distance. The following graph represents the variation of magnetic field B with the distance. In the graph, it is very clear that the magnetic field B is varying directly proportional to the radius small r till small r equals to capital R, the radius of the cylinder. When small r equals to capital R, then the magnetic field becomes maximum. If we go out of the cylinder, that means the distance of the point P is more than the radius of the cylinder, then the magnetic field B is inversely proportional to distance square. Solenoid. This is the next application of Ampere circuital law. Solenoid is a current carrying coil tightly wound into helix. Magnetic field due to the solenoid is confined within its core. Using Ampere circuital law, we can calculate magnetic field in the solenoid. Consider a solenoid having n number of turns per unit length carrying current I. Let the magnetic field due to the solenoid is B. Consider an Amperian loop KLMN as shown in the diagram. Applying Ampere circuital law for the loop KLMN, we get line integration of the magnetic field B dot dl over the loop KLMN can be split as integration K to L B dot dl plus L to M B dot dl plus M to N B dot dl plus N to K B dot dl. In the diagram, it is clearly mentioned that B dot dl over the loop is making different angles at different parts. So let's study the situation. From K to L, the magnetic field B and the length L are parallel to each other. As a result, integration B dot dl from K to L is equal to B dl cos 0. As B is constant, so integration of dl will be equals to L. So we get integration B dot dl from K to L is equals to B into L. This is equation number 1. Now, for length L to M, if we apply the line integration of magnetic field, then we get B dot dl from length L to M is equals to B dot dl dot cos 90, as Lm is making an angle 90 degree with the magnetic field. So B dot dl over the length Lm will be 0. That means the magnetic field will also be 0. Now we calculate for M to N. Integration from M to N over the length B dot dl equals to 0 because the magnetic field outside the solenoid is 0. For the length Nk, we calculate B dot dl. So it will be equals to 0 because again length N to K is making an angle of 90 degree with the magnetic field. Combining all these equations, we get integration B dot dl over the loop KLMN equals to B into L. Again, applying Ampere circuital law for the whole loop KLMN, we get B dot dl equals to mu naught times the number of turns into I. As number of turns per unit length is small n, so integration B dot dl equals to mu naught n L I. Comparing these two equations, we get B into L equals to mu naught n L I. L is common, so we cancel it and we get B equals to mu naught n into I. This is the magnetic field due to the solenoid. If we have to calculate magnetic field at the end of the solenoid, then we observe that the magnetic field close to end of the solenoid is half of the total magnetic field. That means the magnetic field at the end will be equals to mu naught n I divided by 2. Toroid. Toroid is a donut shaped object such as an O ring. It is a ring form of solenoid. It has no ends. Magnetic field due to toroid, if we have to calculate, then using Ampere circuital law we can obtain its value. Let we have a toroid having n number of turns per unit length. Average radius of the toroid is small r. In order to calculate magnetic field, we consider three loops. Consider the loop 1 of radius r1 inside the toroid in the empty region. Applying Ampere's circuital law for the loop, we obtain B dot dl equals to mu naught times I. As current enclosed within the loop is 0, so the magnetic field B will also be 0. Let us consider the loop 2 of radius r2 outside the toroid in the empty region. If we join this loop 2 with the center, then we observe the line joining the center with the circumference intersects the current carrying conductor at 2 points. Once the current is coming outward, second the current is going inward. As current is equal, so the net current will be 0. As a result, the magnetic field will also be 0. Now, consider the loop 3 of radius r in the toroid. Line integration of the magnetic field B dot dl over the loop 3 will be equals to B integration dl, that means B into 2 pi r. Applying Ampere's circuital law, so the line integration of the magnetic field B dot dl will be equals to mu naught times the current into number of turns. Total number of turns of the conductor is n times 2 pi r. So, B dot dl will be equals to mu naught times n into 2 pi r into I. From equation number 1 and 2, B into 2 pi r will be equals to mu naught times n into 2 pi r into I. 2 pi r is common in both the sides, so we cancel it. As a result, the magnetic field B equals to mu naught times n into I. Here n is the number of turns per unit length in the toroid and I is the current. Force on a charged particle while passing through the magnetic field. When a charged particle Q passes through a magnetic field B, then it experiences some force. The formula of the force F is obtained using the following parameters. The force is directly proportional to the charge, it is directly proportional to the velocity and directly proportional to the magnetic field with the angle sin theta. Combining all these parameters, we obtain F is directly proportional to Q V B sin theta. Putting a coefficient of proportionality K equals to 1, we get F is equals to Q V B sin theta. In the vector form, we can write F equals to Q V cross B. The direction of the force is obtained using Fleming's left hand rule. Fleming's left hand rule. It states that if we stretch the forefinger, middle finger and the thumb of our left hand mutually perpendicular to each other in such a way that the forefinger points the direction of the magnetic field, middle finger points the direction of the current, then the thumb will point in the direction of the magnetic force. Today in this session we have discussed about the solenoid, the toroid, the force experienced by a charged particle moving in the magnetic field. In the next session, we will discuss about the cyclotron, about the moving coil galvanometer, conversion of the galvanometer into an ammeter and voltmeter. I hope you enjoyed the session. Thanks for watching.